Okay, I'm going to briefly talk about capturing the digital image, which is chapter 34 in our textbook. Here's some objectives. This is kind of a long chapter, but I'm going to try to condense it down to just 4 objectives. First, we're going to give an overview of digital image creation. That will be kind of a review of material that we've covered up to this point. Then we're going to look at some detailed steps for image creation, both with CR and DR systems. Finally, we'll illustrate the use of the Nyquist theorem for determining spatial resolution, and we'll define some factors that influence the efficiency of digital imaging systems. That will be a place that you'll want to definitely pay attention. So digital image creation, just in review, involves first digitization, and so we'll review how that works and what a dynamic range is. How also digitization is part of how we determine contrast, or how we use digital systems to enhance contrast of the system of the image. Then we'll look at computer radiography and digital radiography, both the indirect and direct capture methods of digital. So digitization basically has 3 steps that occur. First, scanning of the area. So the field of view is placed in a matrix. It's the area that's been sampled is going to be scanned to the matrix, and then sampling. And that means that at each level at which information was inputted on the image receptor, we are going to assign that a pixel value, some intensity number. And finally, we're going to quantify that. So we're going to move from this analog signal to a digital signal which has discrete numerical values that are assigned to every single pixel. So you can see, even as I'm talking about these things, they happen in very rapid sequence. We may not even think about these processes, but each kind of looking at these domains is going to be helpful to us to be able to think, okay, this is happening in the scanning part. This part's this actual sampling, and then this is how quantization occurs with both CR and DR systems. And the dynamic range is just the number of gray shades that any given pixel can represent. And in digital systems, this is always a binary number, and it's what we're talking about a lot of times when we talk about bit depth. So the greater the dynamic range, the longer the grayscale. It's going to have a direct correlation to file size. So file size basically equals the matrix size times this dynamic range, or times this bit depth. And I want to point one thing out. One thing that we sometimes think about when we're talking about dynamic range, there's actually 2 different ways we can think about dynamic range. So I'm going to draw a graph here, and this may be familiar to some of us. This is right here, this is what we call an H&D curve. H&D curve. We use these on film systems, and basically it has a toe section down here and a shoulder section up here, and the dynamic range, and both the contrast and the dynamic range fit within that straight line portion, or that slope portion of the graph. This was very, very helpful, especially in film systems, because in a film system, the shoulder portion, beyond the shoulder portion, was the limits of the dynamic range. So the dynamic range was very much this area right here, and nothing above that or below that. Anything below that, the image would be unexposed, it would appear white. Anything above that, it would be overexposed, it would appear black. So in a digital system, though, we still use this model, but in a digital system, if we were just to look at what the bits are sampling for each pixel, if you will, it would have a dynamic range of one of these numbers here, depending on one of these binary numbers. And by the way, this should be 2 to the 8th, 2 to the 10th, and 2 to the 12th here. So it would have upwards of, maybe even higher than this, 4,096 shades of gray. And so if you can imagine, the curve would just keep on going and going and going, even off the end of this slide, right? So that is a huge dynamic range compared to film's little tiny piece right here, right? So the dynamic range of a digital system is essentially limitless. As long as the computer is sampling, it's going to have data there. But what we do with digital systems is we still apply the H&D curve to this dynamic range in order so that we can see the contrast. We can see this straight line slope here, which is going to be helpful for us determining contrast on the image and appreciating different values and different diagnoses. So we might as well review contrast briefly. When I talk about contrast in a digital system, a lot of times I'm also simultaneously thinking about window width. Um, so the window width is the amount of gray on the image, and it maps directly onto our old friend, the H&D curve. So if I have a steep H&D curve, I will have a very narrow range right here. This would be a high contrast. So it would be a narrow window width, and it would be a high contrast curve that I've applied to the digital image. Versus if I have a more graduated slope like this, all of this right here is useful information. And so this would be low contrast, but it would have a lot of shades of gray as illustrated by this curve. So this would be a wide window width. Now we also talk about level, and a lot of times the way I think about window level is this is the amount of blacks and whites on the image. It's basically, and this scale here actually comes from CT, so don't let that confuse you. But we still apply window width and leveling to digital images. So let's, now that we've kind of reviewed, kind of overview of how digitization occurs and what role bit depth plays in that, as well as the role of contrast and appreciating the images that we've made. Let's get down to the weeds with some computed radiography, and this we're going to go back to the chapter and really think pretty closely about. And I'm kind of going out of order with the chapter pages, but we're on page 596 in the textbook. And the first key term here is the photostimulable phosphor plate, or sometimes called a PSP. It's made of a metastable material, and that just means that the material typically has been doped with europium, and that europium works as an electron trap. Sometimes they're called Farbensenstern centers or color centers, but the idea with these europium portions of the barium fluorohalide or the barium fluorochloride or the barium fluorobromide, whatever other crystal is in this thing, is it takes when the X-rays are incident on the PSP, it ejects an electron from the barium fluorohalide, for example, and that electron gets trapped in this metastable part of the crystal, the europium. The europium traps that electron, right? And so we now have a latent image on the PSP. It's there, the information is there, but it's not yet been sampled, right? So we've not yet done anything in that first step towards digitization, right? Now, when the PSP is stimulated with the helium laser, and like helium neon lasers, they're red, right? They're always going to be red. That trapped electron in the europium is going to be released from the europium, and the crystal will assume its normal crystalline shape, and the action of assuming that normal crystalline state, it's going to phosphoresce, which means it gives off a delayed glow. Now, it's helpful that there's a delay, and it's helpful that it glows, right? Both are important. So this is a phosphorescent process, and that's what we mean by that. Is literally what photostimulable phosphor plate means. Is it means if you scan it with a laser, it's going to give off a delayed glow. That delayed glow is going to be blue-violet, and that's important too. The reason why these colors are important here is because we wouldn't want to sample the laser light with our system. We just want to sample the color that's being given off by the PSP. So what's nice is if you think about the colors of the rainbow, or moving, for example, from ultraviolet to infrared, right? We have the ultraviolet on one end of the color spectrum in terms of wavelength and energy, and the infrared on the other, right? And so if we were moving from wavelength, if we were increasing energies from one side to the other, we would have all the various colors of the rainbow between these two. And so that's helpful because there's basically a gap. I'm not going to be accidentally sampling the laser over here when I'm trying to just sample the photostimulable phosphorescence is being given off by the PSP over there. So that's why that is. I don't want to get too far into the weeds with that, but I think it's interesting. The CR reader picks up this blue-violet light using a photomultiplier tube, or sometimes called a PM tube, and it uses dye nodes to increase the sampled signal strength. Right, it basically adds electrons to whatever it's getting until it has like millions of electrons associated with the signal, and that's occurring as we're sampling the PSP plate with the laser. So here's what that looks like. I just think this slide's helpful. It comes from Bouchon. It's showing that neon helium laser stimulating the europium doped barium fluorobromide. And if you read here, this light emission, I like this slide, in that if you go to, there's a separate part to this, it's giving off a blue light right here. That's actually what's being sampled. That's in the reading part. To erase it, we just expose it to an intense, typically like a fluorescent light, and then it's ready to be used again. All right, that's enough about CR. Let's change gears a little bit and define some terms related to digital radiography, or DR. First thing we'll talk about is a DEL. And this is on page 593 in our textbook. DELs, sometimes called detector elements or DELEX. It's been shortened to just DEL. That means this is an actual element. You can see it. It's very, very small. It's like a microchip. It has three parts to it that are important for us. A detector surface. It has a storage capacitor and some kind of thin film transistor. Now, the matrix of all of these DELs lined up in order to receive information, we'll call an active matrix array. So it's a layer of microscopic DELs. Each one of them contains its own thin film transistor. Each one of those DELs stands for a pixel in the data that we're going to be receiving. So the thin film transistors that kind of connect across this entire active matrix array are just switching gates. Either they are going to read a series, they're going to read any number in the dynamic range of that thin film transistor. So whatever the bit depth of that DEL is, or that every DEL of that active array of matrices, and if I were to draw this, what I'm talking about when I say matrix is almost like a lattice, and each one of these little squares here would represent a detector element or a DEL, and they would all have some binary range of sampling that can occur there. So the thin film transistor is what's going to read out whatever the DEL received during an X-ray exposure. And the fill factor, well, before I get into that, the last part to this is that it has a capacitor, and that capacitor is actually going to be what stores the signal that it's received during X-ray exposure. So the detective quantum efficiency is how efficiently whatever the materials that's made out of absorbs X-rays and produces a digital signal for direct capture, or absorbs light from the crystal matrix and it emits that as information. So we'll get into a little bit more into direct digital and indirect, but just so you know, detective quantum efficiency for direct systems has to do with the ability to absorb X-rays. For indirect systems, it has to do with the ability to absorb light. And finally, there is a fill factor, and that has to do, if you look on textbook page 593, there's a figure 34.2, and it looks something like this. It actually has a very tiny illustration of a DEL, right? And so this part up here is the TFT, and this part down here is what we'll say is the storage capacitor. Everything that I'm shading in blue here would be related to its fill factor, right? And it's important to think about that, because the larger the DEL is, the better its fill factor will be, right? Just due to the limits of engineering. So it would have a higher fill factor. The smaller but the problem is with that larger DEL is it's going to have less spatial resolution, right? We're not going to be able to see little tiny things because the pixels are going to be too big. Smaller DELs are going to have a higher spatial resolution, but they have a lower fill factor, which means that it's possible an X-ray might interact it or it might not. It might miss that surface, just again due to the limits of engineering. So let's look at that in a slice, kind of a side view slice, what that looks like for direct capture. In an instance of direct capture, what we have are X-rays incident on amorphous selenium. So that if you can imagine, this is just a kind of a goop here, right, inside of our DEL, that when X-rays ionize these things, the positive charges migrate down here to the bottom, and the negative charges go up here to like an electrode that attracts them. And these positive charges then are read out, and they're what's stored in the storage capacitor, and then finally switched out through the thin film transistor, if that makes sense. So that is a direct capture system. There are X-rays directly incident on the amorphous selenium, and that's actually what's being sampled. No light is emitted or anything that. It's just electrons and positrons that are being sorted through. Okay, versus an indirect capture system, this is going to have X-rays incident on some kind of crystal system. Sometimes it's cesium iodide, like in this instance, and in this case, what's going to happen is that cesium iodide, it doesn't tell us this here, so I want to indicate something important. Where before we had amorphous selenium on the direct capture system, this is going to be amorphous silicone here. So A-S I believe is the way it's abbreviated, and it's going to capture the light that's emitted by this crystalline cesium iodide, and the light is going to be sent down these light channels to strike the amorphous silicone, and then that amorphous silicone, similarly, when the light hits it, it will produce positively charged atoms, which will migrate towards these electrodes in order to be stored in the storage capacitor and then read out through the thin film transistor. So it's indirect in that it's X-rays to light to signal. Let's talk a little bit about the Nyquist theorem. This is not something to be scared of, but it is helpful in thinking about spatial resolution to think about, okay, now that we've sampled this and we've quantized it, what are some of the weird things that can happen with sampling? And one of the things that I think about, since I ride my bike so much, is if you're watching bike spokes, there's a point at which, as the bike is slowing down or as a car wheel is slowing down, it looks like the wheel is spinning backwards. That's due to the Nyquist theorem. It's because your eye is sampling at a certain rate, and now that the wheel is spinning at close to that rate, to the human eye, it appears to be moving backwards. Same thing can happen with these digital systems. If we're sampling close enough to a certain rate for the digital system, it might result in an artifact. So that has to do with spatial resolution, or SR, and this is equal to the sampling frequency. So it's expressed generally in line pairs per millimeter. And I think we've talked quite a bit about line pairs per millimeter, but I'll draw this out here one more time because it is worth thinking about. A line pair is not just these lines next to each other. It is both the line and the white space. So this is the line pairs, the line and the absence of a line, because in a binary system we work with ones and zeros. So to understand what the spatial resolution will be, we can just say spatial resolution equals 1 over 2 times p, in which p is the del pitch. Now this should be somewhat familiar to us. In fact, if we remember back to CT, we talked about pitch, but I'll refresh our memory just a little bit, and I'm going to draw on this just a little bit more. What we're talking about is if we have these detector elements, right, and they're lined up like we said, right next to each other, and that's how we're sampling and getting a signal. The del pitch is basically the distance from the center of one pixel, or the center of one del, to the next. Why is that important? One way we could also just say it's basically the width of each del. Spatial resolution is inversely proportional to double the del width. Right? I'll say that one more time. That's what this formula, by the way, is saying. Spatial resolution is inversely proportional to 1 times, or to double the del width. So for CR systems that use a very small PSP, if we use a smaller photostimulable phosphor plate, one that fits the anatomy of interest, we're going to avoid histogram analysis errors, right? So I'm just telling you, from the standpoint of both the Nyquist theorem and also spatial resolution, use a CR cassette that fits the anatomy of interest, and not one that's larger than that, because it is reducing spatial resolution. by this formula that I'm talking about. Similarly, if we want to prevent moiré artifacts, this Nyquist theorem is saying that we need to be careful about our sampling frequency because it needs to be at least 2 times the spatial resolution. So whatever resolution we're looking for, we need to have sampled twice that, right, in order to see what we want to see. And that actually stands to reason, right? Because we said it again, it's a binary system. It deals with ones and zeros, and a line pair is both the line and the absence of a line. So if we want to see what we're trying to see, we need both the line and the absence in the line. In essence, we need to be able to sample twice more than what we want to see. So that's as simple as I can describe the Nyquist theorem. Huge textbooks are written on that, but I wanted to make sure that we at least touched on it. And it is helpful to consider that with both digital imaging systems for X-ray as well as digital imaging systems for CT and for radiation therapy and all sorts of different imaging applications. I do want to talk a little bit about imaging efficiency because that is one way that we're limited by these digital systems, and it's a major engineering consideration. The 2 things that I think are most important for us in terms of thinking about imaging efficiency that's discussed in this chapter have to do with absorption efficiency. So how well does the barium fluorohalide or the amorphous selenium or the amorphous silicone absorb information in order to release it at a later time or release it into the TFT. And then the second thing is the K-edge effect. They're both very different things. So I'll talk about one and then I'll switch gears and I'll talk about the other. So for the first, the absorption efficiency. This is the ratio of X-ray photons absorbed by the image receptor to the X-ray photons incident on the X-ray on the image receptor. What does that mean? It means that the image receptor is not going to get all of the X-rays that are supposed to be hitting it, right? So we're only going to be able to sample X number. The less X-ray photons that we're able to sample, the less efficient the image receptor is. And it just kind of stands to reason. If it's not getting all of the X-rays I'm giving it, then it's not very efficient. Either in some part of the crystalline structure or in some part of the TFT, whether it's a CR or a DR system, doesn't matter. I would say that it's lacking some absorption efficiency. The emission efficiency, and this has solely to do with CR systems, is the ability of the PSP to emit light after laser stimulation. So the light emitted it's emitted isotropically from the PSP plate versus going down the light tubes and the cesium iodide. It's emitted in all directions. And this can actually make us lose some information as we're sampling it with the photomultiplier tube. The reason we call that, the fancy word for that, is that it's turbid, meaning that some of the light is actually going to go off in some other direction and not be sampled to the degree that it needs to be degreed. So we would call that an emissions inefficiency, right? Okay, I'm going to change gears now and talk about the K-edge effect, and this is definitely something you want to pay attention to. I'm going way back to physics now, and we're talking about valence shells and binding energy of electrons, right? We were interested in the characteristic X-ray production that can occur inside of the X-ray tube due to K-shell electrons being released from the tungsten target, right? And those are going to produce a characteristic X-ray out of that electron being freed, and that X-ray is going to be called characteristic because it's going to have precisely the binding energy of that K-shell electron, right? Now, the reason we're interested with the K-shell electrons and not the L or the M or the N-shell electrons is because the K-shell electrons are most tightly bound, right? They're the closest ones to the nucleus, so they're being held the tightest, and they're going to release the most energy if those electrons are knocked out of orbit, right? So this K-edge effect is something that happens within the image receptor, right, that is related to whatever the K binding energy is of the receptor material itself. So in this instance here, I have a K-edge effect that's mapped out for barium, because I said that in a CR system, a lot of these PSPs are made out of barium fluorohalide. So the barium atoms that make up that barium fluorohalide crystal that I'm using to sample X-rays, right? They have those barium atoms have a particular K energy, right? If an X-ray photon hits at just that energy or higher than it, it has the power to liberate that electron. If it hits the PSP at an energy lower than the binding energy, it does not have the energy to release that electron. Now you're probably saying, why is that important? Well, the reason it's important is because we get these little bumps. We get these little saw edge effects, right? And that's what we're talking about when we talk about the K-edge effect. That everything left of this little bump here, everything to the left of it, were photons that did not have energy enough to liberate that electron, right? So you can see they were sampled at a rate that was below probably what was occurring. Then once we hit the K-edge, it bumps up and we start sampling at a higher rate again, right? That's a problem. That's a problem because anything to the left of it was undersampled. Anything to the left of that, just to the left of the K-edge, was potentially undersampled, right? So this is a loss of absorption efficiency from the detector element due to a mismatching of the K-shell electron binding energy with the average X-ray energy. Right? I'll say that one more time. The K-edge effect, where it affects imaging efficiency in the image receptor, is that it's a loss of absorption efficiency, and we see that right here. All of this in this little trough is a loss in absorption efficiency due to a mismatch between the average energy of the X-ray beam, right, and this K-edge of, in this instance, barium. Now, there's other K-edge effects, and there's other ways that that characteristic effects play a part in X-ray imaging systems, but this is a primary way that we're concerned with it, is this K-edge effect that occurs at the image receptor. Hopefully this was helpful. I know that some of this stuff is quite at some depth. I would not worry too much about the artifacts, apart from the on page 608, the discussion of the Nyquist versus Moray artifacts. Thank you so much. Bye.